Hi, this is PuyatRanellaGrace Puyat, DSIT, and I will be presenting the third topic in Group 1, which is the EtherChannel and HSRP. Introduction to link aggregation and its advantages. So this illustration is a sample of redundant links with STP by default block. So it is possible to combine the number of physical links between switches to increase the overall speed of switch-to-switch communication. So STP or Spanning Tree Protocol will block redundant links to prevent routing loops. Most configuration tasks can be done in the Ethernet channel interface instead of on each individual port. So EtherChannel relies on existing switch port. So load balancing takes place between links that are part of the same EtherChannel. And the EtherChannel creates an aggregation that is seen as one logical link. And the EtherChannel provides redundancy because the overall link is seen as one logical connection. Implementation and restriction. So this is an illustration of physical port. So you can see that these are the logical port interfaces that is connected to channel group binding. Okay, EtherChannel can be implemented by grouping multiple physical ports into one or more logical Ethernet channel links. And then note that the interface types cannot be mixed. For example, the fast Ethernet and the gigabit Ethernet cannot be mixed within single Ethernet channel. So, if you are going to use the fast Ethernet, you need to use the same link, fast Ethernet on the other switch. So, if you are going to use the gigabit Ethernet channel, and then you should use the gigabit Ethernet channel on the other switch. And then, the full duplex bandwidth is up to 800 Mbps fast Ethernet channel or 8 gigabit S for Giga Ether channel. And then the purpose of this is to increase the speed capability on aggregated links between switches. And then the individual EtherChannel group member port configuration must be consistent on both devices. So, if the physical ports of one side are configured as trunks, the physical ports of the other side must also be configured as trunks. So, within the same native VLAN, additionally, all ports in each EtherChannel link must be configured in layer 2 ports. And then, each EtherChannel has a logical port channel interface. A configuration applied to the port channel interface affects the physical interfaces that are assigned to the interface. And then note that the layer 3 Ethernet channel can be configured on Cisco Catalyst multi-layer switches, such as the Catalyst 3560, but these are not explored in this course. So, a layer 3 EtherChannel has a single IP address associated with the logical aggregation of switch ports in the EtherChannel. So, this is the port aggregation protocol. So, in switch 1 and switch 2 and then the channel establishment, it is said that if the switch 1 is on and switch 2 is also on, the channel establishment is yes. And then if ever that the switch 1 is in auto mode or desirable, and then the switch 2 is desirable, the channel establishment is yes. And then if the switch 1 is on auto and desirable, The switch 2 is not configured, and then the channel establishment is no. And then the switch 1 is on and desirable for the switch 2. The channel establishment is no. And then switch 1 auto on and switch 2 is auto. But still, the channel establishment is on. So, the PAGP is a Cisco proprietary protocol that aids in the automatic creation of EtherChannel links. So, when an EtherChannel link is configured using PAGP packets are sent between Ethernet channel capable ports to negotiate the forming of a channel. So, when PAGP identifies match Ethernet link it groups the link into EtherChannel. So the Ethernet channel is then added to the spanning tree as a single port. So Ethernet channels can be formed by using PAGP or LACP protocol. Okay. And then the PAGP modes are the on, desirable, and auto. The on mode channel members without negotiation or no protocol. For the desirable, it actively asking if the other side can or will participate, and then the auto passively waiting for the other side. Link aggregation link protocol or LACP. So, it has a similarity on the modes of port aggregation, wherein the LACP modes are on, desirable, and passive. So, if the LACP mode is on, the channel members without negotiation is no protocol. And then if it is active or desirable, it is asking if the other side or will participate, and then the passive will passively waiting for the other side. So the following table shows that the possible channel establishment output if the switch 1 and switch 2 is on, and then the channel establishment will be yes. And if the switch 1 is auto passive, and then the switch 2 is active, and then the channel establishment is yes. And then on auto passive for the switch 1 but not configured on switch 2, the channel establishment will be no. And then the switch 1 is on and active for the switch 2, the channel establishment is no. Passive on for the switch 1 and passive for the switch 2, the channel establishment will be no. So, to make it clear, the LACP is a part of an IEEE specification or 802.3AD that allows several physical ports to be bundled to form a single logical channel. So, LACP allows a switch to negotiate an automatic bundle by sending LACP packets to the peer. It performs a function similar to PAGP with Cisco Ethernet channel. Because LACP is an IEEE standard, it can be used to facilitate Ethernet channels in multi-vendor environment. On Cisco devices, both protocols are supported. Note that the LACP was originally defined as IEEE 802.3AD. However, the LACP is now defined in the newer Okay, link aggregation configuration. So this illustrates the EtherChannel form and the EtherChannel not form. So the following guidelines and restrictions are useful for configuring EtherChannel. So the EtherChannel support, all Ethernet channel interfaces on all modules must support EtherChannel with no requirement that interfaces be physically contiguous or on the same module, while the speed and duplex configure interfaces in an EtherChannel to operate at the same speed and in the same duplex mode. So the VLAN match is all interfaces in the EtherChannel bundle must be assigned to the same VLAN or be configured as a trunk. So number 4, or the range of VLANs. An EtherChannel supports the same allowed range of VLANs on all interfaces and in trunking EtherChannel. If the allowed range of VLAN is not the same, the interfaces do not form an EtherChannel, even when set into auto or desirable mode. So this figure shows that that would allow the EtherChannel to form between S1 and S2. So therefore, the EtherChannel will be not formed between the S1 and the S2. Okay. Configuring interfaces. So for in configuring Ethernet channel with LACP requires 2 steps. The first step is to specify the interfaces that compose the EtherChannel group using interface range, interface global configuration mode command. The range keyword allows you to select the several interfaces and configure them all together. A good practice is to start by shutting down those interfaces so that any incomplete configuration does not create activity on the link. And the step 2 is to create the port channel interface with channel group identifier mode active command in the interface range configuration mode. And identifier specifies the channel or group number. The mode active keyword identify this as an LACP EtherChannel configuration. So note that the EtherChannel is disabled by default. So the following commands are the steps in configuring the channel with LACP. So the commands are the interface range and then the fast Ethernet or the port use. So let's say fast Ethernet 01 to 2, and then it will enter the configuration interface range, and then you should type the channel group 1 mode active, and this is to activate the command interface range configuration mode. The mode active keywords identify this as an LACP channel configuration. And then, it will create a port channel interface on port channel 1. It is shown that the line protocol on interface fast Ethernet 0 is set to default down or disabled, and then up after configuring the interface range. And then to check interface port channel 1, and then switch port mode trunk, and then switch port trunk allowed by VLAN 1, 2, and 20. So this is the command if you are going to check the interface status. Just type the show interfaces for channel 1, and then the command to display a one-line summary per channel group is SU indicates use is show EtherChannel summary. And then the next is to display the port channel information, which is you should These are the steps in configuring interfaces. So step 1 is specify the interfaces that compose the EtherChannel group And then step 2 is to create the 4-channel interface with channel group and command in active mode. And then step 3 is change layer 2 settings in 4-channel interface configuration mode. So let us do this in Cisco Packet Tracer. So we are now in S1 and we have to enter the configuration mode. And then type the interface range. Fast Ethernet 0122. Okay. And then channel group. One mode active. Channel group 1 mode active. Okay. Interface. Interface. For channel 1. Interface. Switch port mode trunk. Switch port trunk. Allowed. VLAN. 1, 2, 3. Switch port. Okay. And then let's see. And then show interface. Verify the interface status. Show interfaces for channel 1. Show EtherChannels. And then show channel for channel. So, it is shown that the port channel PO1 is primary aggregator. Group 1 port channels in the group. And then show interface F01 EtherChannel. Show interfaces. AF0122. Let us, since it is not showing the interface of Fast Internet 1 EtherChannel, let us troubleshoot. Okay, show EtherChannels. So the summary is showing that we have LACP protocol at at Fast Internet 1 and 2, and then the output indicates that the Ethernet channel is down. Okay. And then let's show run. Okay, it's now running. And then incompatible PAGP modes configured on S1 and S2. Okay, channel group mode 1 on. Service. Ito. Channel group 1 mode active. Okay. And then next. Let's go back to EtherChannel. Show EtherChannel. Port channel. Okay. Now, it is now showing the group 1 and the port channels, saying that the port security is disabled, and we have the protocol LACP. Okay. And the port state is port channel. That's it. Okay, the next topic is default gateway limitations. Troubleshooting EtherChannel. This is a sample illustration of EtherChannel connecting the switch 1 and switch 2. All interfaces within EtherChannel must have the same speed, duplex mode, native and allowed VLANs on trunk, and assigned to same VLAN. Note that the ports with different native VLANs cannot form an EtherChannel. Default gateway limitations. So this is an sample of router interface, and it serves as a default gateway. It fails. The hosts configured with that default gateway are isolated from outside networks. A mechanism is needed to provide alternate default gateways in switch networks where two or more routers are connected to the same VLANs. Note that the purposes of the discussion on router redundancy, there is no functional difference between a multi-layer switch and a router at the distribution layer. In practice, it is common for a multi-layer switch to act as a default gateway for each VLAN in a switch network. So this discussion focuses on the functionality of routing regardless of the physical device used. This is a sample of one, and if you can see, the switch 1 and the switch 2 as layer 2, and then the route 3 and the router 1 and the router 2 are connected to another one or wide area network. And then this is to implement a virtual router. Okay? Multiple routers are configured to work together to present the illusion of a single router to host on a LAN. The IPv4 address of the virtual router is configured as the default gateway for workstations on a specific IPv4 segment. ARP solution returns the MAC address of the virtual router. And then physical router that forwards traffic is transparent to the host devices. Redundancy protocol provides the mechanism for determining which router should take the active role in forwarding traffic. It also determines when the forwarding role must be taken over a standby router. So the transition from the one forwarding router to another is transparent to the end devices, and the ability of the network to dynamically recover from the failure of a device acting as a default gateway is known as first hop redundancy. So steps for router failover is number 1. When the active router fails, the redundancy protocol transitions the standby router to the new active router role. So these are the steps that take place when the active router fails. The standby router stops seeing hello messages from forwarding router. And the standby router assumes that the role of the forwarding router. And then because the new forwarding router assumes that the IPv4 of MAC addresses of the virtual router, the host devices see no disruption in this in-service. So first hop redundancy protocol, the hot standby router protocol or HSRP is a Cisco proprietary designed to allow for transparent failover of a first hop IPv4 devices. So, the active device is the device that is used for routing packets. The standby device is the device that takes place when the active device fails. And then, the function of the HSRP standby router is to monitor the operational status of the HSRP group and to quickly assume the forwarding responsibility if the active router fails. The HSRP for IPv6 is the Cisco proprietary HSRP, provides the same functionality of HSRP but in an IPv6 environment. While the Virtual Router Redundancy Protocol version 3 is a non-proprietary protocol that dynamically assigns responsibility for one or more virtual routers to the VRRP routers on the IPv4 LAN. One router is elected as the virtual router master, with the other routers acting the backups in case the virtual router masters fail. The VRRP version 3 is the capability to support the IPv4 and IPv6. The Gateway Load Balancing Protocol or GLBP is a Cisco proprietary HSRP that protects the data traffic from failed router on a circuit allowing load balancing between a group of redundant routers. GLPB and IPv6 Cisco proprietary FHRP provides the same functionality of GLBP. HSRP defines a group of routers, one active and one standby, and the virtual IP and MAC addresses are shared between the two routers. To verify the HSRP state, use the show standby command. And then HSRP is a Cisco proprietary as we have mentioned earlier, and VRRP is a standard protocol. So this is a sample illustration of HSRP overview. So one of the routers is selected by HSRP to be the active router and default gateway. So the R1 or the router 1, let us assume that this is the active router that the HSRP has been selected. And then if in case that the other router will become the standby router, and this is the R2. And if an active router fails, standby assumes the role of an active router and default gateway. So, if in case that R1 fails, R2 is ready to serve as the active router from being a standby router. And then the hosts are configured with single default gateway virtual address that is recognizable by both the active and standby routers. Okay. HSRP versions are version, and then the HSRP version 1 and version 2. So the difference between the two, when we talk about the group numbers, the HSRP version 1 is 0 to 255, while the version 2 is 0 to 4095. And when we talk about the multicast address, the HSRP version 1 is 224.0.0.0.2, while the version 2 is 224.0.0.102 or FF05 semicolon colon 66. So virtual MAC address, okay, the last two digit groups are number, and then in version 2 the last three digit groups are number. And then the support for MD5 authentication, the version 1 is not supporting the MD5 authentication, while the version HSRP priority and preemption. So, role of active and standby routers determined by election process. By default, the router with the numerically highest IPv4 address is selected as the active router. And control the HSRP election with priority and do not use the highest address. The HSRP priority is used to determine the active router. And then the default HSRP priority is 100. And the range is 0 to 255, and the router with the highest priority will become active. Use the standby priority interface command. The HSRP preemption ability of HSRP router to trigger the re-election process. And to force the new HSRP election process, preemption must be enabled using the identify preempt interface. So the router that comes only online with the higher priority will become the active router. And the HSRP states are the initial, learn, listen, speak, standby, and active. The initial, this is the beginning state. It indicates the HSRP is not running. It happens when the configuration changes or the interfaces is first turned on. And then the learn state is the router that has determined the virtual IP address and has not yet seen an authenticated hello message from the active router. In this state, the router still waits to hear from the active router. And then the listen state is the router that knows both the IP and MAC address of the virtual router, but it is not the active or the standby router. For example, if the three routers is HSRP group, the router which is not in active or standby state will remain in listen state. And then the speak state is the router that sends periodic HSRP hellos and participates in the election of the active and standby router. In this state, the router monitors hellos from the active router and will take the active state when the current active router fails. No packet heard from active router. And then the active state is the router forward packets that are sent to HSRP group, and the routers also sends the periodic hello messages. HSRP timers. The active and standby HSRP routers send hello packet to the HSRP group multicast address every 3 seconds by default, so that the standby router will become active if it does not receive a hello message from the active router after 10 seconds. And you can lower these timer settings to speed up the failover or preemption. However, to avoid the increased CPU usage and unnecessary standby state changes, do not set the hello timer below 1 second or the whole timer below 4 seconds. The HSRP configuration command, the first step is to configure the HSRP version 2, and then the second step is to configure the virtual IP address for the group. And then the step 3 is to configure the priority for the desired active router to be greater than 100. And then the step 4 is configure the active router to preempt the standby router in cases where the active router comes online after the standby router. To figure this is the command syntax used to complete the configuration steps. So these are the router config, standby version 2, and then standby, and then the group number, and then the IP address. And then standby, the group number, the priority, and the priority value. And then the router, standby, group number, and preempt. So each command have their function and definition. So the standby version 2, it configures the HSRP to use the version 2, of course, because by default the HSRP version is using the version 1. So sa next step is for the standby group number and IP address, it configures the HSRP virtual IP address that will be used to specified group, and no group is configured. Then the virtual IP address is assigned to group 0. And then the next command, standby group number and priority, and the priority value, configures the desired active router with a higher priority, the default priority of 100. So range is 0 to 255. If no priority is configured, or if priority is equal, then the router with the highest IP address has the priority. Okay? And then the standby group number and preempt, it configures a router to preempt the currently active router. So now I am going to show you how to do it in Cisco Packet Tracer. Okay. Hi, this is an example of an HSRP topology. We have here the R1, the R2, and the virtual router. and then the internet connection connected to other server, and then the switch 1 and 3 computers client that are connected to switch 1. So I will be showing you how to configure the HSRP. So in R1, we're going to I will exit it first. Okay. And then enter the configuration and then interface F00, and then the IP address given is 172.16.10.2, and the subnet mask is 255.255.255.0, and then standby version 2. Okay. So I have entered the standby 1 IP and then 172.16.10.1, which is the IP of the virtual router, I mean. And then the state is standby active. Okay. And then we are going to enter the standby 1 priority 150. Okay. And then standby 1 preempt. Okay. And then no shutdown. Okay. Now, and then exit. Okay. Now we are going to configure the R2. So same procedure. I'm going to exit this first for you to see the first step. Okay. So enter the configuration terminal, and then going to enter the interface. Since I am using the fast Ethernet 00, and assign the IP address 172.16.10.3, and then the subnet mask of 255.255.255.0, and then standby version 2. Okay. Okay. Have to correct this little error. Version 2. Okay. And then standby standby 1 IP, and then the 172.16.10.1. Okay. You will see that HSRP Fast Ethernet 00 states okay in it. Okay. And then no shutdown. Okay. Exit. Okay. then next, we're going back to R1. And then show standby. Okay. So now we can see that the state is active and the virtual IP address is 172.16.10.1 and the active virtual MAC address is this. Okay. Going to get the output and display in this part, and then you will also see that the preemption is enabled and standby router is 172.16.10.3, which is the router 2. So it will be, so in this topology or in this network, the R1 is our active router, while the R2 is our standby router. Okay. Let us get the virtual IP address and the actually this is for this this is the MAC address of the virtual router. So I'm going to delete this. Okay, so and then replace it with this. Okay, and then now we are going to repeat the same process to R2. Show standby. Okay, so the state is up. The state is standby. So it confirmed that our R2 or router 2 is the standby router. So 7 state changes and the virtual IP address is 172.16.10.1, which is our virtual router here in the middle. And then it is said that the preemption is disabled and the router standby router is local. Okay. And then next, show standby brief. Okay. So this is the output of that command. So let us check if the state is active. So it is the F001 is active and local, and the standby is that 172.16.10.3, which is our router 2, and the virtual IP is the 172.16.10.1. Okay. And then we are going to repeat the same process to R2. Show standby. Okay. So it indicates that our fast Ethernet 001. Okay, next, the HSRP debug command. So in R2, we are going to type the debug standby and then question mark. And then, it will give us the packets, HSRP packets. Okay. Okay. And then, debug standby packets. Okay. It is indicated that HSRP packets debugging is on. And then, it is giving us this output. And we should wait until it is done. Okay. Troubleshooting common HSRP configuration issues. So use the debug commands to detect common configuration issues. HSRP routers are not connected to the same network segments, although this could be a physical layer issue. It could also be a VLAN sub-interface configuration issue. HSRP routers are not configured with IPv4 addresses from the same subnet. HSRP hello packets are local and they are not routed beyond the network segment. Therefore, a standby router would not know when the active router fails. HSRP router are not configured with the same virtual IPv4 address. The IPv4 address is the default gateway for end devices. And HSRP routers are not configured with the same HSRP group number. With this will cause each router to assume the active role, and devices are not configured with correct default gateway address. And although not directly related to HSRP, configuring the DHCP server with one of the real IP address of HSRP router would mean that end devices would only have connectivity to remote networks when that HSRP router is active. Okay, the new terms and commands for this module is Port Aggregation Protocol or PAGP, IEEE 802.380, First Hop Redundancy Protocol or HRP, Standby Router Protocol or HSRP, Active Router, the Standby Router, the Virtual Router Redundancy Protocol or VRRP, and Link Aggregation Control Protocol or LACP, ICMP Router Discovery Protocol or IRDP, Master Router, Backup Router, and Gate Load Balancing Protocol or GLB.